We were ready.
We were, but Marcelo jetted off.
He'll be back in a sec, I'm sure.
He's trying to...
Okay, well, good morning, everybody, or wherever you are, good day. My name is Steve Gordon. I'm the current chair of the HPC Education Chapter. And this morning, we have a group from University of Toronto that will be talking about trends and strategies in advanced research computing education. So I'll leave it up to you guys to introduce yourselves and go ahead.
Sure. Well, good morning, everyone. My name is Marcelo Ponce. As Steven was mentioning, we work at Scinet, which is the supercomputer center here at the University of Toronto. We are really excited about talking about the educational endeavors that we do here. So we are part of the core team that does that. So probably we can introduce all of ourselves.
Yeah, okay. So my name is Ramses Manzon, and I'm also an analyst here at Scinet and part of the education effort as well. That's me.
My name's Eric Spence, and same as Ramses, I'm part of the teaching staff here, as well as an analyst at Scinet.
And I'm Danny Gruner. I'm CTO at Scinet, and I'm the chief cheerleader for these guys.
The most important and beautiful one. I'm the only one we have so far. So, in any case, thank you so much for the invitation and for the interest in what we do. One of the things that I should mention, and this is a personal feeling, but I think I share with my colleagues here, is that we do this with a lot of passion for the training and the education, and because we really like to do these kind of things. So we are going to be talking about different things, or at least different topics. So let me first starting by introducing a little bit about what Scinet is, if you don't know about us. And I ask you guys to please, if I forget something or I, not saying something properly, just talk. So Scinet is as I mentioned at the beginning, is the supercomputer center at the University of Toronto. We are really proud to be the home for the largest supercomputer in Canada, and this is particularly true this year when we have launched our newest and largest supercomputer, Niagara, at the beginning of 2018. But it was true before, because we have a system called GPC, General Purpose Cluster, which started in 2009, I think, roughly. Yeah. We were at the top 20 in the 500 fastest supercomputers at that time. The nice thing to notice is that since the very beginning of operations, at that time, 2009, we already had a strong commitment towards teaching and training and education, if you wish. And these guys can talk better about that than me, because they were here since the beginning. And I think Eric and me joined Scinet around 2014, 2013, something like that. In any case, many of the courses that we taught and that we teach, or that we taught at the very beginning, were training for new or non-experienced users. And I'm going to talk a little bit more in the next slide about that. By the way, if you're interested to know a little bit more about our system, if you go to the slides, which I think I can make available, send to Steven or something, there's a hyperlink there. It takes you to a blog where we basically tell the story of how Niagara was deployed. There are some videos there. It's kind of fun. So a little bit of motivation and background. So, and I think this picture is quite generic for many supercomputer systems, or at least the trend that we have seen how HPC has evolved, at least in academia and research environments. We all noticed that at the very early times in HPC, systems were put together by researchers using just basically commodity components, right? Like one group doing some calculations, chemistries or astrophysicists, bring together a bunch of components, they create their own tiny cluster, and they were happy and they could do things with that. Now, the nice thing of that is that basically all the knowledge, all the requirements, and all the operations of these systems were basically relying within the group that created these systems. So that was useful because, if there was a graduate student that was graduating and there was a colleague there or postdoc, that kind of knowledge was transmitted and kept locally within the groups. Now, however, what has happened in the last 10 to 20 years is that the demand for these computational resources has increased quite a lot. There are different reasons for that. More specialized and faster components like chips or circuitry has been cheaper. So creating and building better computers was possible. There is also the increment in the amount of data that the different fields, and not only now the traditional fields, but many other fields, as we're going to discuss later on, has seen. So this idea of these tiny clusters has evolved into shared clusters. And now, what it was before just property of a tiny group within a department, now is probably, or evolved into clusters from the department. Not much later, this cluster from the departments evolved into clusters into the universities, and then these universities get together, create a consortia, like SciNet, for instance, and after that, we start to share these resources at the national level. So this is all well and good, because it means that there is more computational power available for doing research, for the researchers, for the groups. But there are also some caveats here, or some challenges. And one of those challenges is that the knowledge required to operate these equipment and to program and get some science done, it does not reside anymore with these groups or labs, right? These are more specialized equipment. So that part of this in-home or in-house knowledge is gone. At the same time, because these equipments are more specialized and powerful, non-traditional fields were given access to these new systems, like think about biology or soft sciences, if you wish. But the problem here is that they lack the proper training or knowledge in how to use them, because basically no one within their groups have been trained for doing so. So this is a bit of the motivation of the teaser of why we have started teaching. At the moment that SciNet was created, there were a few supercomputers that were launched at the same time, but there were the goal and the task of our team was to make these resources available for many different departments, basically all the departments across the university, but not only the traditional academic department, but also the associated hospitals. So the question was, how can we train people from different fields? How can we offer them to run in our systems if these people has never been exposed to systems like that? And not only that, there are challenges like programming, transferring the data, all kind of things, and probably many of you are aware of this. So what I want to show you now is how we have measured, how we have observed or perceived this trend in the last probably 6-7 years. These plots are up to 2017. The next ones will be up to 2018, but basically you will see kind of the same trend. So the first thing I want to mention is what we're going to show different indicators of how we measure the participation in our courses. The first one, hello, yes? Okay. The first one is what we call attendance hour. And this basically measures one person attending 1 hour of training. If you wish, this is a measurement of the effect of teaching and an indicator of the demand for a particular course. So what you see on the left is a plot describing the attendance hours. On the x-axis is the different years, so starting on 2012 up to 2017. So you see basically 4 shades or 2 colors and 2 shades each of them. The yellow one represents what we basically denote as scientific computing courses. You will find there courses related to C++, to numerical libraries, to high-performance computing. The red ones are what we call data science courses, things like computational statistics, machine learning, those fall under that category. Now, you will notice that there are 2 shades for each of these colors. There is the non-credit and the credit one. So the ones that says not for credit means that these courses cannot be taken or are not recognized as part of university credit courses. the ones that says for credit is because students can take it, if there are graduate students, they can take it as part of their curricula, either in the master program or the PhD program. So if you look at the plot on the left, what you can see is a clear increase in the demand, basically, of these courses. And what you will notice is that actually both data science and scientific computing are increasing at the same time. And it's almost exponential the way it's growing. Now, I should warn you, this is not, or I think I mentioned this, the scientific computing ones also include the high performance computing. So in the next slide, we're going to basically divide the scientific computing ones into the actual scientific computing courses and high performance computing courses. Now, the right plot, what it shows is the average number of students in our courses. And as you can see, there's something interesting here also to notice is if you compare to the previous plot where both attendance hours were increasing, here what you see is that the number of students in the data science course is increasing, while the number of students in the scientific computing course may have reached this critical mass or average mass or plateau, if you wish, which is around 25, between 20 and 30, because it oscillates every year, and we notice that in our courses directly. So let me go to these other plots. They are kind of similar in the sense that they still show growth. Again, attendance hours is the measurement of how many hours a person attending the courses has taken. The other concept we want to introduce is the course hour, and that is a measurement directly of how much teach we do. It's a measure of the teaching effort, if you wish, and it's equivalent to 1 hour in which an event, and we're going to describe which kind of events we have, has been held. So now the left plot, which is also the attendance hours as we were showing before, is divided in these 3 categories. That is the main 3 categories that we have for our courses. High performance computing courses, think about MPI, programming, OpenMP, CUDA. Scientific computing, as I was mentioning before, any kind of things that related to numerical implementation, number crunching. To be honest with you, the division between scientific computing and data science at some point is kind of it's a very thin line, and one need to be careful what call one thing or the other, but we managed to, at least in the courses, differentiate that. And then the data science, as we were describing before. So one thing that you should notice as well is, and probably that was also the case in the previous plot I forgot to mention, is that our data science courses started in 2015. So after noticing the need for these courses, and this is kind of a funny story because I'm reminded every day at home, my wife tells me, oh, you started the courses because you realize that I don't know anything about statistics. Well, she doesn't say it in that way, but kind of like that. In any case, we started the data science courses in 2015, and you can see they catch up very quickly. The nice thing of these plots are a bit more up to date. They reach up to 2018. You see the growth as well. You notice here more clearly that the number that has basically remained constant is the high performance computing courses. That's the blue bar at the top, and that number more or less remains the same. And the scientific computing kind of like that, it oscillates a little bit as well. Now, if you look at the course hours, at the training effort, you will see that, again, this trend holds. And again, the one that keeps growing is the one on data science. So every year we add or we create some new courses targeting this data science. And now, you know, data science includes things not just analyzing data or parsing your data or curating your data, but also techniques like machine learning, neural networks, those kind of things. So I mentioned that we have different type of events. So I'm going to quickly describe the main ones that we have. So we have seminars. These are mostly 1 hour long events where there is it can vary. It can be a technical talk by one of our users. It can be a presentation from a researcher. Sometimes what we have been doing lately, and I kind of like that format very much, is if we have a student that had taken our courses and that student is working in a particular project that has benefits or direct benefits or implications from the courses, we invite that student to make a presentation about that. Usually goes under the name of SNAGs, which stands for Signed User Groups Meetings. And it roughly happens once per month or once every 2 months, depending on how busy we are to organize things. The other type of events are workshops. These ones are usually short in the sense that it's 1 day training. It can go from 3 up to 6 hours of training. Again, these are particular or specialized training events. We have our own workshops, like we have workshops on large scale data, file I/O, or machine learning workshops, those kind of things. But lately, what we have been doing also, and you will start to notice a pattern here, is partnering with different departments, some of them at the university, like the Fields Institute, which is one very well-known mathematicians institute. I always mess up this one. Creative Destruction Lab, very fancy name. These guys started an initiative to create a program in quantum machine learning. So we are not in the quantum realm yet. We might at some point, but our part there is to give some instructions about basic machine learning techniques.
They're sort of an incubator of
startups. Yeah.
Trying to get into that field.
Exactly. And we have others. So there is a chemistry, biophysics symposium that every year we are invited to teach different topics. So these kind of workshops are quite interesting. They allow us to reach more people, and it's a way to advertise our other courses. So it's a win-win situation, we think. Now, the next 2 ones are within our main success. The first one, and they are not necessarily in chronological order. So the first one, our main, our main source of revenue in terms of courses, if you wish, is our graduate style courses. And we have 3 of them right now. They are the 3 codes right there: FE 1610, EES 1137, and MSN 1090. So the first one is for the physics department, is a scientific computing course for physicists explicitly, although we not only get students from physics, we get the students from many different departments, including engineering, computing science, computer science, and others. EES is another interesting one, because what happened is that the University of Toronto has 3 different campuses across Ontario, the province. One is in downtown, the city of Toronto. The other one is in Scarborough. It's a city that is, 2-3 hours away from here. And the other is in Mississauga. It's another city towards the other direction. In any case, this course is specialized on quantitative applications for data analysis. It's sponsored by the Department of Environmental and Physical Science at the Scarborough campus. And the third one, which we're going to discuss a little bit more in detail later on, is the MSN 1090. Is a course that is our latest course. It was created 2 years ago now, I think, or last year, sorry. Is a computational biostatistics course, and is sponsored by the Institute of Medical Science. The other important avenue of teaching that we have is the summer schools, and this has been true almost since the very beginning of SciNet. It's our flagship event, probably. And we're going to talk a little bit more about that. It's 1 week long intense training during the summer, usually the month of June or July. And it has been growing like crazy in the last years. Finally, we have collaborated also with undergrad courses. Again, the physics department, a prof at the physics department has approached us, and we were guest instructors in an undergrad course that it was quite interesting, because it's a course that the undergrad physics students takes at the very end of their undergraduate career. They teach them different tools like writing reports, presentations. I think they do some sort of internship in different labs. So our task there was to basically teach them scientific computing techniques, to teach them some data analysis techniques and some visualization techniques. So we were invited to teach, I think, 8 weeks, something like that, 8 to 10 weeks.
Yeah.
And so we basically split as we wish the topics. And the nice thing is that, well, this prof is deeply involved in the LHC, the Large Hadron Collider experiment. So he's a very avid user of SciNet, of our supercomputer. So it was a good excuse for us for also getting their students trained and starting using the supercomputing as well. Even when the students were not directly related to particle physics, some of them were doing biomedical or biophysics, so it's still quite interesting. And the other thing that we do, kind of related to training, is outreach. We do a lot of outreach. Just this week, last Tuesday, we have, what was that, Danny, the fifth big data big data challenge for high school students, where high school students are presented with real data, and there is an open set for them to analyze, digest the data as they wish. So it's kind of fun. We participated also in the Science Rendezvous, which is a sort of door opening event across the university, across the city, where we had a stand, we talked with people, kids, and we had some nice games where people can play and connect with the idea of parallel processing and parallel computers. So that is a little bit of training format.
It might be nice to, these are all kind of connected, right? And they flow in one another. So we started doing multi-day workshops, which turned into our summer schools, but those multi-day workshops, some of them became just single-day workshops. And then at those workshops, students might say, hey, it's hard for me to sort of book off a whole day. What if you could give this as sort of a graduate style courses where there's a lecture every week? So some of those workshops got turned into short courses, like 4 weeks, 2 lectures a week, something like that. And then they would take those courses and ask their departments, hey, can't we take these for credit? Since the physics and astronomy were one of the first to say, yes, that's fine, we can do that. We'll call them mini courses. They already have something like that. And so from workshops to sort of per week, so weekly events, it turned into a graduate style course. And then those turned slowly into term-long courses. And the last few courses have actually just been created as graduate courses because departments go, hey, you guys do this. This is great. Can you do it for us? But it starts from a grassroots. That we see what's needed. We give a workshop. We see that it actually could turn into a course, and then that's how it progresses. So all these things are sort of intertwined.
Yeah, it's quite interesting actually, because it even happens in some departments like EB, ecology, evolutionary biology, that the first approach or the first response from the department was, oh, no. Bio students don't need that. What happened after is the students came to the courses and went to the graduate coordinator and said, no, we want to take this course. So the graduate coordinator came back saying, yeah, okay, let's then take the course. So yeah, it's a very, very interesting and organically way to grow this course. So just to give you a feeling, and we're not going to read all this, this is a kind of, and I don't think it's complete neither, it's a list of the courses that we teach. The ones that are at the very top on the left column, that are kind of in bold, are the graduate courses we were just mentioning before. The other one that probably is good to underline is the ones related to AI and machine learning. So those has been spiking in interest. But as you can see, we have also more technical and specialized courses like GPU programming. And many of those, or some of those, actually we do in collaboration with other departments or colleagues. So we had a limited number of well, it's basically us and probably 1.5 more person that can help with the teaching. Sometimes we involve some of the sysadmins if they are keen to teach some Linux or something like that. But basically, we had a very limited number of us that can do the teaching. So this is a bit the other big thing that we have, which is the summer school. So this table represents, let me try to describe that. On the right side, you have days. So it goes from the 1st to the 5th day, so 5 days of training. And then each of the columns represents a track. So the students can select which track, actually not the track, they can basically select which course they want to take. So we try to categorize them so to make it easy for people to understand what is going on or what are the topics. So the first column represents the high performance computing courses, second data science, and the third one biomedical algorithms or techniques. So the HPC is the typical MPI, CUDA, OpenMP, programming that you will deliver to the students. The data science one has a little bit of everything, has introduction to Linux shell, R, Python, machine learning and neural networks, of course, some visualization. And then the bringing your own code is more like an open session for discussing problems and advising students. Oh, I had to tackle this data, I had to tackle this problem. How will approach that? It's more like a hackathon kind of thing. The third one, which is a very interesting one, is biomedical or bioinformatics. And again, it has a bit of everything: MRI analysis, RNA sequencing, peelings, next generation sequencing, data sets or public data sets for neuroimaging, and some hacking. The interesting thing to mention, in particular for the biomedical and the CUDA part, is that we do that in collaboration from colleagues from, in particular, the biomedical, the Center for Addiction and Mental Health here at the University of Toronto. That has been true for the last 2 years. So we started this initiative in 2017. We repeat this in 2018. We have 300, how many students we have this year?
What was it? 200 and something. 200 and something.
So it's very popular. It has been growing since the very beginning. Just to give you an idea, what was that, 2009, 2010, the first summer school? It was basically restricted to the first column. In 2013, I think, 2014, 2015, we added the second track, data science, and in 2017, we added the third track in bioinformatics. One thing that we haven't mentioned yet, and this is tied to what Francis was mentioning, is our certificate programs. So we offer 3 certificate programs. And as you can imagine, these are tied to the type of courses that we teach. So there is the high performance computing, the scientific computing, and the data science certificate. The requirement is that the students has to take 36 credit hours of training. And the hours of training are counted like this. If the course or the event they are participating is a short course, then 1 lecture hour corresponds to 1 credit hour. If these are long courses, and long courses can be either the mini courses or the full graduate courses, because those mini courses usually involve 1 weekly assignment where the students has to go and actually implement some codes, then the lecture hour is equivalent more or less to 1.5 credit hours. So a 24 hours long course, which is a full semester course, is equivalent to 36 credit hours. So with that in mind, and one thing that is worth to mention is the reason why I think the idea of the certificate started is because, well, we had these training events at the very beginning, right? Like the students come here, they get the training, they can run their programs in the supercomputer. It's all nice. But at some point was like, okay, how can I get some recognition that I was there, that I participated, that I had gained these skills? So in an effort to basically reward that, we started issuing these certificates. Now, the interesting thing that has happened, and what you can see on the plot on the right, is the evolution of, or the number of certificates that we have issued in time. So starting in 2013, where we basically have only 2 certificates, the high performance and scientific computing, it has, or probably we start recording these trends in 2012. We start seeing how this number of certificates has increased, and probably you remember how we have issued at the time, or not?
How many? Or?
How many, yeah.
well, right now it's at 200, as you can see.
Okay. So yeah, this is cumulative. So we have 200 certificates issued, I think, at the moment. Now, the other interesting thing is that you can see at some point there are bumps. And this is probably when one of the graduate courses ends, because that gives enough credits to students to request one of the certificates. The other thing you will notice is, as we were mentioning before, the data science courses started on 2015, but it's one of the fastest growing certificates. So probably going to catch up the other ones quite quick. Want to add anything else to it?
Yeah, it's nice because people can take all of the courses together, and they are in demand.
Oh, yeah.
I'd say about 75% or so people actively ask if they already can have their certificates. The other ones we just give them because they earn them.
Yeah, they reach the number of points.
What is interesting to see here, and maybe Marcelo will come back to that later, is that it seems like the trend for HPC has stopped, but we can't distinguish that from the trend of us being only so many people. And if we teach more data science, we tend to teach less HPC. The number of people that come to it is similar, but it gets harder and harder for people to complete their HPC certificate because there's only so many courses.
That's very true. I don't think I will come back. It probably was something I should have pointed out in the previous plots, but that is quite true. The other thing that is worth to mention, and for this we don't have like quantitative data to represent, but we have anecdotal comments, is that these certificates have helped students with shop applications or those kind of things. So we truly believe this is useful for them. So let me switch a little bit gears, or not completely switch gears, but talk more in detail about one of the courses, the graduate courses that we created, and this is the Computational BioStatistics course. And what you can see there is another kind of plot with the distribution of students that we get from the different disciplines, and we make a very coarse aggregation of the disciplines of the fields. So we have sciences that include chemistry, physics, astronomy, astrophysics, even biology, I think. Then we have medicine and public health. And then we have engineering and others, we have some even students from philosophy, economics, or humanities in general, if you wish. So one thing that is worth to notice is that medicine and public health, and this, I will come back at this point at the very end, is roughly 35% of the population of students that we have. And this, at least for me, is quite surprising. So this is kind of a justification, if you wish, for why we created this course, plus the road that Rancis was mentioning, how these courses have evolved. So we know that proper training in data analysis, and in particular statistical techniques, is crucial. And we recognize that there are several courses at the university, mostly taught by statisticians or the math department. However, the thing that we recognize as well is the way these courses are taught is not in a practical manner. It's not in a way that the students can get that information and directly apply to the problems they have. And even more, when we teach this course, we notice the weakness in some of the students related to the mathematical background they should have. So with that in mind, we consider creating this course in collaboration with the Institute of Medical Science at the University of Toronto. In addition to that, as we mentioned before, we had a scientific computing course for physicists and the quantitative applications for data analysis. And many of the things I'm going to mention for this particular course apply also to these other courses. There are tiny variations, mostly on the topics, but I think the strategies and the techniques that we use are basically the same. So related to this course is a 12-week course with basically 2 one-hour lectures per week. The final grade of the course is based on approximately 10 assignments, 10 weekly assignments. There are no finals. However, I should mention that for the first time, although Rancis tried this before for your introduction to programming course last year, we will have a midterm, an online in-class midterm, just to be sure, that the students are up to date with the material and they are digesting the material properly. Actually, we will have the midterm for this course next week, right? So that will count as one more assignment, so 11 assignments at the end. The passing mark for the course is the average of the 10 assignments and the midterm in this case, and it should be greater than 70% is the standard policy at the university. The interesting thing also from this course that deviates a little bit from the other ones is that we have, so this is the third term in a row that we are delivering this course. In the previous two terms, we had 60 students in each term, and this term, we have 80 students. So there's no way this course is stalling in any manner with respect to the interest that the students have. The other two courses, just to give you an idea, the average number of students is between 20 and 30, I think.
Yeah. Also steady, but at a different level.
Yeah. The assignments and examples, and this applies also to the other two courses, are designed to cover study cases based on the topics of interest related to the students. So in this case, it's medical study, drug trials, DNA analysis, ChIP-seq, all these kind of things. Similarly for the quantitative applications for the analysis and for the scientific computing for physicists. On the right, you can see a kind of a very short summary of the topics that we include. We start, just to scare them from the very beginning, we start with the introduction to the Linux shell. Then we continue with best practices in programming, version control, defensive programming, modularity. Then we start with R, an introduction to R, to programming, conditional loops, functions, scripts. We review some basic statistics, and we take as an excuse to do it in R. We go to more advanced stats. We discuss some important points in statistics because, as I was mentioning before, we had noticed that some of the students lack of proper training on these techniques. And we also give them some basics on machine learning and neural networks. We discuss visualization techniques, how to generate professional quality plots and plots that they can use in their manuscripts, in their papers. And by the end, in the last week, we discussed some high performance topics like memory management, file I/O, and even some distributed computing using R. What kind of strategies we use, and this is again true for all the courses that we have, and it's one of our main way to get into. The important thing to underline here, perhaps, is that by creating these graduate courses that are available for the students taking any master or PhD degree at the university, is that now they have a wider cross-section. It means that many more students can see the courses and they can enroll. There are some caveats there, but we will come back to that. But the main or the most important probably element, I think, for getting into the university curricula is partnering with institutes. As employee, we are a staff at the university, so we don't have any kind of faculty position. But I will come back to that. But we don't have any kind of faculty positions that allow us to create courses out of the blue. So we need to partner with different institutes in order to allow us doing that. One of the things that we also get by partnering with the institute is that now to basically recognize our situation, we are being hired as sessional lecturers. So that put us in a kind of official position within the university. The other thing that is very important is that it allows us to hire teaching assistants. And this is crucial because it's tied to the way that we deliver the courses. As I mentioned, we have 10 assignments. The assignments are always coding assignments, so they have to come back with proper script, function, or piece of program that actually do something. So grading, as you can imagine, 60 to 80 codes per week is quite a challenging task. So that part is done by our TAs under our supervision and instructions. We provide rubrics and we provide examples of the solutions, but we need the TAs to do that. So the departments also pay for the TAs in this case. I mentioned we had 2 lectures per week. The lectures are a combination of hands-ons and workshop styles depending on the topic that we are covering. One of the things that we had noticed as students or engage the students a lot is when we put assignments, and we had 2 or 3 of these assignments, that we ask the students to use their own data. So basically, you can develop tools during the course to tackle their own data. That has several benefits. It shows the student of how to implement and incorporate best practices techniques in the set of tools they develop. It also allows us to get insights into the students' work. And related to that, we also have one assignment where we basically ask them to produce a professional quality plot using scripts, and again, using their own data if that is possible. The other thing I should mention, I don't think I have a slide for that, but this we have been noticed lately, and it has been true in several cases. It allows us to start collaborations with different groups within the university. And I will touch upon that point at the very end, but that is also a very interesting way to engage with different departments and different students. The tools that we use, we have a lot of tools online, a lot of resources. We use our own education website, which Francis is one of the developers, I think, at this point. Yes. So if you are interested about what courses we teach, just go to courses.scinet.utoronto.ca. I think the framework is based on ATutor. Mm-hmm. It's an open source framework. All the materials is available there. We have the slides, we have the scripts, we have the assignments. All our lectures are recorded, so you have access to the recording as well. There is a forum, there is a chat. In addition to that, we offer copious amounts of office hours for our courses. And as I mentioned, we use the help of the TAs for grading the assignment. The evaluation methods, I think I mentioned this, is mostly based on the assignments, and we strongly believe this is the best case for reinforcing the learning and for the students to learn, because these, again, are practical skills that they cannot learn otherwise. We've designed these assignments with 2 major goals in mind. Practice the concept that we presented in class, but also we usually like to include some sort of hidden message, something that the students will need to digest in the material, in the data, so that they have to think, they have to develop this kind of critical thinking skills. As I mentioned, there are almost 10 weekly assignments. If one of the assignments is not good, the students have the choice to, or the option to have a make-up assignment to recover a week or missing submission. There is a late penalty policy just for guaranteeing that we have submissions in a timely fashion. And the marking and the grading is done by our TAs under our close supervision. And of course, as you can imagine, there are a lot of logistics involved on this, but it's doable. So just let me, and I think we are like roughly at the 45 minutes, so I think it's a good point for discussing a little bit some things and start the conclusion. So basically, designing a course like this, as well as the other 2 courses, allow us to innovate and transgress into this kind of non-traditional fields or disciplines. The other thing that allow us to notice, and this is also of a lot of interest for the departments sponsoring these courses, is some diagnostics information about the students' performance. And this goes beyond the particular technique that we teach. It also touches upon topics like analytical skills, critical thinking skills, those kind of things. I mentioned this quickly. It's a way to establish collaborations. We have examples where we have collaborated with students developing bioinformatics pipelines or data analysis wrappers, where we end up being co-authors of the papers. But also, and Eric, if he wants, can say more about this, he has been one of the instigators in a recent paper in cosmology, where these 2 students taking his course developed a novel technique in neural networks, just being inspired by the course, I think. We have, the university has independent survey that runs in each course, and all our courses has been participating in this. And all this survey shows the appreciation and level of satisfaction from students taking the course. And to be honest, it's quite amazing to see that. I think I mentioned this. This course in particular is the third term that is being taught, and it's still in high demand. This year we have a waiting list of 15 to 20 students. That already was a huge headache. But the important thing to underline here is, and I wanted to mention this one more time at the end, is the need for this kind of training. As a summary to all our educational and training effort, I would say, well, we had these 3 graduate courses at the University of Toronto in these 3 departments. We have our 3 certificate programs, also very much appreciated by the participants. And we'll have our summer school with 3 parallel streams tackling traditional HPC, data science, and bioinformatics. And this is one of my final slides. The other 2 are just references and resources. And this is just fresh out of the press. Yesterday, we were at the IMS, Institute of Medical Science, 50th year anniversary conference. It was an international conference. The pictures that you see there, I apologize for the quality, was taken with my BlackBerry, which is still pretty much alive. So the quality is not as good as you may want, but the pictures there are from the main presenter, the keynote presenter. And the interesting thing here, and at least that surprised me very, very nicely, is that even in the medical community, people is starting to notice that there are changes. There are changes that are coming, and they are upon us already. So what these 2 slides shows is, I don't know if you can see that, but on the one on the left, is how the physicians see the organization of the biomedical science change, like the research clinicians changing approach. So on the left, you see the traditional one where you have trainees, you have a staff scientist, the PI, and then bottom-up approach. The right one is the new one. And one thing I want to emphasize is this block here, data analysis. If you go to the other slide, you will notice as well that it's hard to read from here, but there is also data analysis techniques like omics in the sense of genomics and all these kind of things. So one of the patterns that we recognized in that conference, and it was kind of international, so there were people from Canada, but North America, United States as well, is the need of this field for people trained in computational data analysis issues, computational statistics. They don't have people doing that. They don't have the knowledge. They even have or know very well that bioinformaticians are very much on high demand, that they are very well paid. We were there with Danny, and we speak with 10 to 15 people from Canada and from United States. And I was surprised to see how eager they were for courses like this and for training like this. So if you are in my message here is, if you are in a supercomputer center associated to a university, go and talk with your friends or colleagues at the Faculty of Medicine. You will be surprised, I was surprised yesterday to notice how much demand there are for courses and for interactions between disciplines offering this kind of training. That's the last part for me. I only have 2 more slides. These are resources pointing to our education website, to our courses in particular, to the framework that we use, and then some final references. These are 4 papers. Wow, 4 papers. 3 of them are going to be published this year in the Journal of Computational Science Education. The one at the very top, Rances, is going to be presenting at one of the workshops in supercomputing, the one on Monday, the whole day on Monday. So if you are interested to hear more about that, we have more stats there, more numbers, more interesting results. We invite you to stop by if you are at supercomputing. I don't know if you guys have anything else to add.
We do have a few questions also, but go ahead. You go ahead first.
Yeah, just wanted to add that this idea of interdisciplinary nature of science these days is not just a buzzword anymore. I did the analysis of trying to break down our students by discipline. And in some cases, it was just plain impossible to say if they were biologists, physicists, whether they were in medicine or computer science, because they were doing everything. So it's just...
And one thing I would like to emphasize is the courses that we teach are practical courses. So it's not like we're teaching statistics in a theoretical sense. We're teaching the practice of statistics. The same is true for bioinformatics. We would teach the practice of bioinformatics for scientists who need the tools. And that's a big difference in the approach that is traditional at universities.
Yeah, absolutely. There are a couple questions here that some of which you answered in your presentation, but one has to do with who pays you to teach all these courses? How does the financing of this work?
Danny pays.
Now, this has always been the catch, let's say, with what we do. So we are paid to run the Supercomputer Center and to do user support. So we very early on found out that our bandwidth for one-on-one user support is very limited. As you can imagine, we're a small group. All told, with sysadmins and everybody, we're order 15 people, not more. So we early on, as I say, our motto became that the best way of doing user support is by teaching. And I think it's that's a truth, right? You teach the users. It's the old adage of teach a man to fish kind of thing.
Yeah.
And it actually works. So when people tell us, oh, but you're not paid to teach, we say, well, we're doing training, user training, call it what you will. It's what has produced the most bang for our buck and the best results. There was an issue with teaching for credit at the university because we are not really allowed under our contract to do that. But the way that these courses are being compensated from the university is the guys are what's considered sessional lecturers. So basically temping. They're moonlighting. They're really working more hours than anybody should. But it's, this is the way we've evolved, right? So that's basically, in a nutshell, what happens with compensation.
Yeah. Okay.
It's tough.
Yeah.
Yeah. The growth, if I may add, the growth is so that most of the courses were taught as training sessions anyway. So that was sort of covered by our primary mandate. The growth in the number of students is what really was tough because, as Marcelo said, grading 80 pieces of code every week is impossible. So having the TAs be paid by the other departments, so having a separate budget for that, makes that growth possible. There's no way we could have really managed to grow that way without that support. And similarly, to get, since a large fraction of these students are now not direct users of us, having that being paid as sessional lecturers make that component, let's say, above board.
But every user that you teach that ends up running their stuff on their laptop is a little bit less load on our very overloaded systems anyway. And at the same time, if they do end up having very large data or heavy computational projects, they know where to come. And they are, again, they're well trained already. So it's a win-win. Doesn't matter which way you look at it.
Excellent. There were some other questions. I think you addressed them with your presentation. Are there any others out there? You have a couple of very good compliments on your presentation, so thank you very much for that. Any other questions from anyone else? You can either put it in the chat screen or you can unmute and ask them directly. Well, if not, so you'll send me these slides because I can post them on the website.
Yeah, for sure. I will like right away.
So for your information, within the next couple of days, We will post your lecture to YouTube as part of the CHPC Education YouTube channel, and we'll send you the link to that as well, so that you'll have that as a record.
Excellent. Great. All right. Thank you so much. Thank you for inviting us and for having us. It has been a pleasure.
Well, thank you again for your presentation. We very much appreciate it. And thank all those who attended, and have a good rest of the day. Thank you.
Thank
Thanks.
you.
Thank
Bye-bye,
you.
guys.
Bye.